So hi everybody, thank you for being here today. Again, another game theory seminar, and today it's with Johannes Hörner. Big pleasure for me to introduce Johannes. We know each other for a long period of time.
And he's one of the greatest economic theorists, doing in particular repeated games. So he was teaching this week at the Moroccan Center of Game Theory, repeated game with infrastructure monitoring. So Johannes, so there is it doesn't work very well. So Johannes, so he's French and German. After HEC in Paris, he was in Penn State University doing his PhD. University of Pennsylvania, UPenn doing his PhD. Then he was assistant and associate prof, I think, at Northwestern before joining Yale University as full professor. And he was at Yale for a long period of time, so I did know him from when he was there. I was even visiting him at Yale for a period of time. Now he came back to France at the CNRS at Toulouse School of Economics, where he is now.
Thank you.
So, and give you the floor.
Thank you very much. Thank you for these very kind words. Thank you all for being here or being on Zoom. It's a pleasure. And just one correction, it's not that I was teaching, I am teaching this week. All right, just for those of you who are attending, the lectures were not done. All right, it goes on until Friday. All right. So it's a pleasure being here, and no, I will not surf, but I'm happy to bargain. This is joint work with Paolo Nucic, who is a young AP and assistant professor at the London School of Economics. I will not give you a long introduction. The motivation will come a little later on. It depends on how much I run out of time, but I think the game is enjoyable per se. I call it, well, the subtitle is The Imposter Syndrome, a User's Guide. Sometimes you feel like you don't know what you're talking about, and the question would be, what do you say in that case? All right, so let me just present the game in a very simple way, and we'll then discuss applications afterwards. It's a very simple game that we want to study. We will study several variations of it. Let me give you the simplest one, all right? And you'll see that we can complicate it in many ways. If you know of any related models, I'd be very grateful. It goes without saying that it's work in progress. There's some extensions, some generalizations we don't know how to deal with. So we'd be delighted if you have any feedback, comments on this project. So I just pushed on the wrong button. So think about two debaters, all right? And there's one judge. I use the judge because of the letter J, and it's convenient because my debaters will be I, player 1 and 2, all right? Now, I call them debaters, you can call them politicians, and the judge, I want to think about it as an audience member, the public, you listening to those two debaters. And one of them is an expert, the other is a quack. If you're not familiar with the word quack, it's someone who doesn't know what he's talking about, all right? So someone knows something, and the other one doesn't. Now, something is modeled by a state of the world, and I'll just use the simplest distribution to begin with. For most of the talk, we can discuss complications later on, but let's think about the state of the world as being something that is uniformly drawn from some interval, m greater than 1 for most results. Sometimes I want m greater than 2. It really doesn't matter very much, but think about the state of the world could be something between minus something and plus something, and they're all equally likely. All right? It's not on a circle, it's on a line, and you know the bound m. Now, the debater knows the state, the other has no idea, and more importantly here, I'll assume that one of the people is, whoever is the expert knows is the expert, whoever is the quack knows is the quack, and they know who's who. All right? So I'm debating with Rida on, I don't know, Moroccan politics, and you're trying to figure out who knows anything about Moroccan politics. It's common knowledge among the two of us that he's the one who knows about it, but the judge does not know. Okay, yep. The example with Rida is probably not the best because we all know who would know better, right? Sorry? There's another Rida, exactly, right? There are two Ridas, and now I really don't know who's the expert in Moroccan politics, all right? And I have, as a judge, to come up with a choice, right? You might think about this as politicians, as I said. I have to say, I think we should, I'll go with Rida number 1 or Rida number 2. I think he's the expert, all right? So the game will be a game of, from the judge's point of view, picking one of the two, choosing who he thinks is the expert. Clear? Right? So the motivation, I'll come back to it, is that often the issue that prevents the learning to acquire information about important issues is that they just don't know who's the quack and who's the expert, right? It's a fact that, say, in the United States, many people think that RFK Jr. is just as expert in vaccines as Anthony Fauci was. And that makes it very difficult for a random person to learn whether vaccines are a good thing or a bad thing, all right? So the ignorance of the judges, of the audience about who knows what he's talking about and who's not, is a significant obstacle to learning about anything such as vaccines or states of the world more generally, right? So the idea was precisely to understand how these two types of uncertainty, the one regarding who is actually a quack and who's the expert, and the uncertainty regarding are vaccines good or not, what's the state of the world in this abstract form, how they interact, all right? How they interfere and how they prevent learning, possibly, and how different people, depending on how little or how much they know to begin with, about either the state of the world or about who's an expert and who's not, how it changes how much they learn over time when they listen to debates. So I skimmed over it, but I'll assume that the judge assigns equal probability to the expert being player 1 or player 2, okay? Okay, what makes the expert an expert, as I said, is that he knows the state of the world and the quack has no idea, all right? If I have time, I'll talk a little bit about cases where the expert is not perfectly informed and the quack isn't perfectly ignorant. But here, let's just take that as a starting point, all right? The quack has no idea what he's talking about. The expert knows exactly the state of the world. Just to be clear, the expert is no saint. He wants to be selected. If lying is useful for that, he will lie. Similarly, my quack is not stupid. He might be ignorant, but he's not stupid. He'll say whatever it takes to be chosen. Okay? Now, this is too simple at this stage. I'll just introduce one additional piece of information, namely what the expert knows. I'll assume that while he doesn't know who's the quack and who's the expert, he does get to see a private signal. He's not entirely clueless. He has maybe relatives who had measles, or he knows a little bit about Morocco. He flew to Rabat. He has a little bit of an idea about things, how they happen here. So I'll assume that what he sees is omega plus epsilon, where epsilon is a uniform draw between -1 and 1. The judge. The quack knows omega. Okay, the quack knows omega. The judge, he observes S, which is a noisy version of omega. Clear? You don't perfectly know omega. If you knew perfectly omega as well, then obviously listening to the debate would be pretty pointless. But on top of that, it would be very easy for you to identify who's the expert. There would be an equilibrium where the expert truthfully announces omega. You know omega because you'd see it, so you'd select the agent saying omega, and the quack would have no shot because the quack doesn't know omega, and there are just a continuum of possible omegas. So if he says something at random, there is no way it's gonna work. All right. Now, For historical reason, we picked this noise to be normalized to have support -1, 1, and the state of the world being in -mm. Perhaps it would have made more sense to think about m being 1 and 1 being m. What really matters is the ratio of those two, which measure how much knowledge you have relative to the uncertainty there is in this game, right? So 1 over m measures how precise your information is relative to the uncertainty in the game. Clear? Yep. So, yes, this microphone works occasionally. Maybe it's selecting what I say. So, what happens in the simplest version of the game, it's an interesting game, I think, because one of the motivation was how should we structure debates? If we have Fauci engage in a debate with RFK Jr. and they're being asked questions about the state of the world, you know, what's the efficacy of the vaccine against measles? Should I first go with one? Should I first ask the other one? How should I structure the talk? We'll talk about that. For now, let's just assume that talk is impolite, as Aumann would call it. They both simultaneously speak up, all right? They just both say something. Talk is cheap. They say whatever they want, and I'm going to assume that what they say is just a real number. Okay? Clear? Having listened to those two messages, one round, the judge decides who he picks, and what he wants, as mentioned, is to pick the expert. All right? His objective is not necessarily to learn the state. The objective for him is to learn who's the competent person, because for some reason maybe he's the one that he wants to elect to the office. All right? So the payoffs are very simple. The debater gets 1 if he's picked, whether he's the quack or the expert. The judge gets 1 if she picks the expert and 0 otherwise. So it sounds like a zero-sum game, and in some ways it is similar to a zero-sum game, but it's a 3-player game, so it certainly is not zero-sum. All right? Because we have 3 players. But what should be clear is that the expert and the judge have perfectly aligned interests. And the quack and the judge have perfectly diametrically opposed interests. Clear? So if we fix the if we fix the expert, say, to, for instance, tell the truth, we would be facing a 2-player game between the judge and the quack, and that one would be a zero-sum game. Clear? So the question is, what are the equilibria of this game? I can't call them the value because there are multiple equilibria. It's not zero-sum. But I'd be interested in equilibria in general and how much we can extract information both about the state of the world and about who's the expert. So the solution concept, this is an extensive form game. We could use refinements. Let's just think about the simplest game whereby the quack and the judge choose messages optimally, given that using Bayes' rule, the judge will form his posterior belief regarding who is the expert and pick whoever he thinks is the most likely to be the expert. So there is no commitment. The judge will pick whoever he thinks is the expert. And so I'm using what is called the perfect Bayesian equilibrium concept. What the quack does, remember the quack has no prior information to begin with, so he's choosing a distribution over the real numbers. All right, he picks a number at random, possibly, which is what he's going to say. The expert, he has a collection of distributions because he knows omega. So for each possible state of the world, he might use another distribution over messages that he utters. Clear? The judge, he has listened to message of player 1, of player 2, 1 being the quack, 1 being the expert. Who's who? That's not clear. And he has his own signal, which is omega plus epsilon, and he chooses player 1 or player 2. Clear? Is the game, is there anything Clear? Okay, so if you want to solve that, the first thing to observe is, as mentioned, it's not a zero-sum game. There are lots of equilibria. There are some which are utterly uninteresting, those that are called babbling in the literature, those that carry no information. For instance, if both debaters are supposed to say at random a number between -1, m and m, so they basically say something at random which could be a state of the world, but they say it in a way that is independent of the state of the world, as far as the expert is concerned, because he knows the state of the world. Then listening to the two messages is totally useless for the judge when it comes to deciding who's the expert and who's the quack, because he knows that what he's listening to is unrelated to their identity to begin with. He's indifferent, therefore, whether or not those messages are consistent with his own signal or not, whether they're inconsistent with omega given his own signal S or not. He doesn't know who's the expert. He doesn't know who's the judge, and therefore he might as well choose at random. And that's not an interesting equilibrium. The question is whether we can come up with more interesting equilibria. So the next one I want to talk about is the one I call the signum equilibrium, and that's just slightly more sophisticated, just to show you that some information transmission here is possible. For instance, the expert could just say the state of the world is positive or the state of the world is negative. And if the expert does that and the quack picks at random either positive or negative, after all he doesn't know, and both announcements by the expert are equally likely, then from the judge's point of view, one of two things can happen. Either both debaters report the same sign, in which case he might as well choose at random because it's not very useful, or they report opposite sign, and he might as well go with the one whose sign matches the sign of the signal he receives, because all things considered, it doesn't take much computation to figure out that this is the more likely one to be the expert, given that the expert is reporting a sign that is the one of the true state of nature. Clear? Right? So Rida says, if Rida is the expert, he says +1 if omega is positive and -1 if it's negative. Rida number 2 doesn't know. He just says +1 or -1 is probability 1/2, 1/2. And I listen to those signs and I pick whoever has the sign that matches my own signal sign, provided, of course, one of them says one sign and the other one says the other. All right? It carries a little more information. An obvious question is, can you do even better? Could we go further? Could we do something finer that carries more information? If one of the Ridas is actually the expert, could he tell me the state of the world? Is there an equilibrium where someone who's an expert is not only an expert, but he's an honest expert? All right? So let's try that. Wow, that was... Thank you, guys. Having fun in the back? It's just like that? Okay. So, it's a dangerous thing. Okay. So, let me try to construct an equilibrium. It's just a tentative equilibrium, okay? Let's just try to go for a candidate equilibrium where the expert tells the truth no matter what the truth is. So whenever the state is omega, whatever omega is, his distribution is just the Dirac distribution on omega. Okay, if it's 0.5, he says 0.5. If it's minus 0.7, he says minus 0.7. And let's assume, because that seems to be the reasonable thing to do, but we'll come back to it, let's just assume that if truly indifferent, the judge picks at random 1/2, 1/2. All right, if he's indifferent, right? So if his posterior is that both Ridas are equally likely to be the expert, he picks at random 50-50. Let's just maintain those two assumptions and see where it takes us. Well, what I want to argue next is it takes us nowhere. There is no such equilibrium. Let me explain why. And let me assume that there is such an equilibrium and see what the problem is. Well, to that end, let me just introduce one more definition, which is when is a message by an expert, by a player, consistent with the signal of the judge. I'll call it consistent if it's within 1 of his own signal, right? Which makes sense because remember the signal of the judge is the state of the world plus minus epsilon, where epsilon is in 0, 1. Yep? Uniform. So if truly the expert tells the truth, then his message is automatically consistent with your own signal, right? It's conceivable he's the expert if what you hear from one of the players is within 1 of your own signal. If on the other hand you know that the expert tells the truth and you hear one of the players send a message that is more than 1 away from your own signal, you know he's a quack. Clear? So for sure one of the 2 messages is consistent. Possibly both messages are consistent. If only one message is consistent, then it's the expert and we're done. That's the one you pick. If both are consistent, it's a little trickier. If both are consistent, you're going to have to think about, well, considering that the state of the world is equally likely to be one of those 2 messages given my own signal, would it be more likely that the other message was sent by the quack if the quack is number 1 or if the quack is number 2? So I'm going to have to compare the probability with which the quack would send each of those 2 messages, given that the expert is equally likely to report those 2 messages, given that the state of the world is uniformly drawn. So let's go down this way. Well, the first observation I want to make is that it's kind of obvious the quack wants to randomize over everything in minus m to m. Now remember, the expert tells the truth. So clearly you don't want to say something which is not in minus mm, because that would basically be saying I'm the quack. All right? And you don't want to, as a quack, leave out some messages, because if not, such a message would be so tempting for the quack, because if, let's say, message 2/3 is not in the support of the distribution of the quack, then saying 2/3 as a quack, well, you might be unlucky and you might be inconsistent, but conditional on being consistent, the judge would immediately say, ha, he's the expert because the quack never says 2/3. Okay? So if the support wasn't the entire interval, then it would be, by contradiction, too tempting for the quack to say those messages that are precisely outside the support, because conditional on the event that it turns out to be consistent, they would definitely be such that the judge just picks you. Okay? I would just say when I started this paper, I was really interested in the problem from the judge's point of view, but for some reason suddenly I felt much closer to the quack and wondering how should I behave, all right? And very quickly I started thinking, gee, what should I do as a quack, all right? And the judge came second in my line of thought, which is why the subtitle, The User's Guide as an Imposter, all right? The expert also turns out to be utterly uninteresting. We'll see later on that, you know, judges, I mean, experts are just hopelessly honest in those games. They just, the interests are aligned. It's terrible. All right, so this is the support of the quack. The next thing I want to say is the quack has no atom in that distribution. Again, the intuition is pretty obvious. The distribution of messages by the expert has no atom, because the state is randomly drawn uniformly between minus and mm, so no particular state has a positive probability. So if there was an atom by the quack at, let's say, 1/3, then saying 1/3 would just be equivalent to saying, I'm the quack. Clear? Because even if you're lucky and it's consistent, the judge would just think about, well, 1/3, how likely is it from the expert? Like 0, all right? And how likely is it from the quack? Well, some discrete probability, he's the quack. So there cannot be an atom. You can refine a little bit to figure out that actually it has to be absolutely continuous with respect to the Lebesgue, with respect to the uniform, so you also need to have a density. So what's the density? It's not going to be shocking what density you're going to use. let me just argue that this density must, well, before I go that, let me first argue that the payoff is bounded away from 0. So as a Quack, you must get some positive payoff. Suppose not. Well, think about picking the message that minimizes the density. Okay, if there is an infimum, who cares? It's no big deal. Well, think about this as being achieved. So this message, if it's consistent, you're gonna be thought as being very unlikely to be the Quack. Because as mentioned, if your message is inconsistent, you have no shot anyhow. But if your message is consistent, and remember, the expert's message is consistent, who's gonna win is going to be a function of what's the probability with which the Quack would have used one of the messages versus what's the probability that the Quack would have used the other message, because the expert is equally likely to have sent both messages because both states are equally likely. So if you're using a message that minimizes the probability with which the Quack sends that message, then you at least tie with the other message that the expert sends in the event that both are consistent. So you'd win with probability 1/2 at the very least if you're lucky enough to have chosen a message M here that was consistent. And the probability of consistency is bounded away from 0, right? It's pretty easy to figure out what's a lower bound to the probability that your message is consistent. All it takes is that the state of the world is sufficiently close to the message you sent. So your payoff is bounded away from 0, and who cares about the constant? It is bounded away from 0. What it implies is that the Quack's density not only must have full support, but it must be flat at the top. So what I'm arguing is it can't be, and I apologize for anyone who's on Zoom because I'm going to use the board here, it can't be that my density, here's minus m, here's m. Let's say that it looks like that with a flat point right there. It could be flat, but then, but it can have a max, only there's a max. But what I'm arguing is it must be flat over some set of messages. Not necessarily an interval, but it cannot be having an argmax which is unique. Okay? Why? Because that message is a message you're supposed to send. But if you send it, then first of all, if you're inconsistent, again, you're losing. But even if you're consistent, let's say if that's the message you use and the expert uses this message M prime, really the expert will say, well, how likely is it that the Quack sends this message versus how likely is it that the Quack sends this message? Well, he's more likely to send this message M, so when I listen to M and M prime, I'm going to go with M prime. He's the one who's more likely to be the judge. Okay? So the only way you could possibly win is if M prime was precisely as likely to be sent by the Quack as the message as you're sending right now. So it would better be the case that those messages that have the same density as yours, the same level of density, those messages, they must have a measure which is strictly positive within 2 of your message, because those are the messages that are relevant given the consistency requirement, conditional on which anyhow it is necessary that your message lies for you to actually get a positive payoff. Is that clear? So we need to have something with flats, but then we're going to get a trouble one step further. So let me call S bar this set of messages that maximize this density. As mentioned, a message within that set must be such that within 2 of that message, the set of messages that are also in S bar is strictly positive. So you must tie with positive probability with other messages that you could possibly use as a Quack. But I'm arguing that unless this flat is everywhere, so unless you're using the uniform distribution, we're going to be in trouble. Because if it's not the uniform distribution, so let's say we have a flat here and we have something here there, maybe it's continuous, maybe it's not continuous, I don't care. But what I'm arguing is sending this message relative to sending this message is a much, much better idea your payoff will discretely jump up by sending this message relative to this message. Why? Because they're equally likely to be consistent within epsilon. But for any other message here that the expert might tell, from the judge's point of view, when he compares, are you the one sending M prime or are you the one sending M? It doesn't matter how close those densities are. What matters is whether one is greater than the other. M prime in my picture is strictly more likely to be sent by the Quack than M. And hence, if both messages are consistent with the judge's signal S, he will go with whoever sends message M. But obviously, that means that this M right there is strictly better than M plus epsilon, because M plus epsilon is strictly higher. So we cannot, so the argument is just slightly more involved. It's just considering a sequence that converges to something in S bar and arguing that we have an issue with the continuity in the payoff. In fact, the payoff should be constant because we argued that the support is the entire interval. And all it takes for me is to argue that the payoff can be constant along that sequence. In the limit, it's going to go up. Clear? So the only candidate, remember we're trying to prove a contradiction here, but what I've argued, and for now I haven't used much in terms of assumptions, but all I've argued is that the unique candidate strategy for the Quack is the uniform distribution. And that's not shocking. That's probably what most of you would have guessed. If you don't know, you might as well replicate the marginal distribution with which the expert is uttering the states of the world, right? That's what all imposters, Rida looks at me noddingly, he approves, right? When you don't know, just say something that is plausible. If the uniform distribution is the plausible one, use the plausible distribution. The problem, though, here is that while this means that conditional on both messages being consistent, the judge is indifferent, and therefore he picks you with probability 1/2, you as the Quack, the probability that the message you send, the probability that it is consistent, is not constant on minus mm. Right? If I ask you, what kind of message are most likely to be consistent with the signal of the expert, of the judge, you'd argue 0. Okay? In fact, given that everything is uniform, it's not just 0, it's everything over some interval. But the extreme messages, those close to minus m and m, are less likely to be consistent with the signal of the judge. Right? If you say something extraordinary, you're less likely to be consistent with what a given judges know. All right? And people ask us, why didn't you work on the circle? Precisely because we think that it is true that some messages are just more likely or less likely to be consistent with what people get as information about the state of the world. All right? So why does that matter? It matters because it means that because the probability of consistency is not constant, you can't be indifferent over all messages if conditional on consistency you're being picked with probability 1/2. This is where I'm using probability 1/2. I said, right, conditional on being consistent, you're winning with probability 1/2, but the probability that you're consistent is not constant. Problem. So it bothered me because unlike all these eminent people in this room, I am not a zero-sum specialist, and I like to think about equilibria existing, and so I thought there is something awfully wrong with my algebra. Where in those 4 steps am I going wrong? And I'm not going wrong anywhere. Where I'm going wrong is that it is true that fixing the expert strategy, namely telling the truth, we're dealing with a zero-sum game between the judge and the Quack, but I can't restrict the strategy of the judge to just be either pick player 1, pick player 2, or pick 1/2, 1/2. Okay? What we need is a convex set of strategies to get existence. So we need to allow the judge, in case he's indifferent between 2 messages, to break ties whichever way he wants. Clear? Conditional on the judge doing so, we certainly will have an equilibrium of the game between the quack and the judge, fixing the expert to truth-telling. Clear? Now, let's look into that. Let's suppose that now, in case both messages are consistent, and again, that's the only case of interest, given that the expert reports truthfully and hence his message is automatically consistent, suppose that the judge can break ties whichever way he wants. Let's also assume there are lots of ways to proceed from here. Let's assume that it treats players symmetrically. What it means is that the probability with which he picks one of the players, probability with which he picks Rémi, in case Rémi says one message and Sané says another, is exactly the probability that with which he would pick Sané if those messages were just flipped, right? So players are treated symmetrically. Then there exists a unique Eklund strategy for the quack, and that follows from the first 3 steps in the proof that I've sketched, the proof of non-existence. So nothing has changed. It is true that the quack must be randomizing uniformly over all messages. What is not true is that the judge must pick, in case both messages are consistent, both players with probability 1/2, 1/2. Which type of message should he kind of reward? Well, given that the more extreme your message is, the less likely it is to be consistent, it must be that in case an extreme message is nonetheless consistent, it's likely to be picked to compensate for the lower probability that it is consistent in the first place. All right? So the judge will favor whoever sends a more extreme message whenever those 2 messages are consistent, and therefore whenever the judge is actually indifferent between the two debaters. So it doesn't mean that we have a unique tie-breaking rule. We still have a lot of freedom. Now, again, in terms of linear algebra, these are infinite systems because everything is in the continuum, but truly the judge has 3 arguments he can condition his choice on: the message of player 1, the message of player 2, and the signal he got. Of course, it's only interesting when those 2 messages are consistent with S. But truly what we need to make sure is that the quack's utility be independent of the message he sends. So his expected utility relative to his own message should be constant. So it's a marginal condition. If you really want to write this explicitly, it's an integral over the message sent by the expert, which follows the distribution of the state of nature, and a second integral over, given the state of nature, the signal of the judge. And that double integral must be such that once we integrate out using the tie-breaking rule phi, the payoff is constant. So you've got lots of degrees of freedom. It doesn't mean that solving for a single tie-breaking rule is easy. Fortunately, it is possible, and there are many special cases that are actually relatively tractable. For instance, he could decide to use a tie-breaking rule that only depends on the larger of the 2 messages. You can write down this indifference condition and explicitly solve for it. Let me just illustrate what it looks like for this maximum tie-breaking rule. So in this picture, phi of M1, M2 is the probability of picking the debater whose message is the largest when you only condition on the larger one of those 2, and of course when those 2 are consistent. So this would be, if the larger of the 2 messages in absolute value is 0, then clearly the smaller one in absolute value is also 0. Then this starts at 0.5. And this, again, is the larger of the 2 messages, conditional on this larger message being consistent and the smaller message being consistent as well. This picture depicts the probability with which the player sending the larger message is being chosen. It's above 0.5. This is an illustration for m being 3/2, so we can compute precisely. If you send an extreme message, well, it's quite unlikely to be consistent, but conditional on consistency, it wins the day. Clear? Okay, now I fixed the expert strategy. Might go back and ask, is it optimal for the expert to report truthfully? And magically, yes, it is. And it's not a fluke. It's not just true for the uniform distribution. Loosely, it was not obvious to us, by the way, because given that exaggerating, remember, larger messages are more likely to be picked. So if you're the expert, you know this curve, and you know the state is 0.8, yes, it's pretty obvious you don't want to say 0.79. That's pretty stupid, right? There's a slight chance that you become inconsistent, right? Because it could be that the expert signal is 0.8 plus 1, and then 0.79 suddenly makes your message inconsistent, while by telling the truth, for sure you're consistent. So by saying something slightly less, you might turn out to be inconsistent. Plus, even if you're consistent, you're going to decrease the probability with which you win. That sounds pretty stupid, all right? But saying 0.81 sounds not a stupid idea because, yes, there is a slight chance your message becomes inconsistent, but at the same time, conditional inconsistency, you increase the chances with which you win. But remember, the Quack doesn't know really, he has not such a good idea about how his message affects the probability of consistency as you do, because you do know the true state. And yet he's indifferent across all messages. You know exactly the marginal probability with which exaggerating by a little bit makes your message less likely to be consistent. Yet, because the Quack was indifferent, you're not. You prefer to tell the truth. This is not a great intuition because the players are not symmetric. I can't just say because the Quack is indifferent, the expert should prefer to tell the truth. Because the Quack is facing the expert faces the Quack. It's a bit magic. Okay? But as I mentioned, it turns out that from the expert's point of view, telling the truth is optimal, having solved for this tie-breaking rule. All right? Again, the equilibrium is not unique. In the class of all equilibria, all I've said is, suppose the expert tells the truth, let's solve for the equilibrium between the Quack and the expert, and the Quack and the judge, and let's prove expose that the expert telling the truth was optimal. And the tie-breaking rule that I picked played no role. Any tie-breaking rule that makes the Quack indifferent will have the property that the expert wants to tell the truth, which is quite remarkable. Yep.
Question.
Yes.
Since it's the judge who chooses somehow the tie-breaking rule, so he's kind of the only choice here. What is the best?
Very good. We'll come to that. Thank you for asking. Let me just do some obvious comparative statistics, partly that motivated the work. So one of the motivations, well, I'll come to it in a second, was to understand how the informativeness of the public affects their learning from messages. So there are two types of things we can learn about: who's the expert and what's the state of the world. And both might be interesting depending on the context, right? Maybe I truly want to know what's the interest rate next year, but truly maybe I couldn't care less and I just want to know who's the best transfer banker for the Fed, all right? So these are two different questions, and I can compute the payoff of the judge as a function of 1 over m, namely the quality of his signal relative to the uncertainty in the game. Not shockingly, the more precise the signal of the judge relative to the uncertainty that prevails, the higher his payoff. All right? That is not answering your question just yet. It's just saying something that is kind of obvious. The more informed you are, the better you're able to discriminate between the two agents. More interestingly, though, is your belief about the state omega. Now, this is a more complicated calculation. I need to normalize it. But even so, what I really want to figure out is, given that you have some information to begin with, S, how does the belief you have about omega depend on the equilibrium that is being played? So what I'm going to think about is, this is the estimate of the state given all the information you have, and I'm going to look at the variance of this. All right, so I'm going to ask, how much does the variance of your posterior belief depend on M? All right, which is a measure of how much you learn from the game. Okay? And what I'm going to argue here, well, it follows from the calculation that it has an interior maximum. And what the intuition is the following, which I thought was quite interesting, and indeed, as I said, was the motivation was to say that if someone really has very poor information about the state of the world, if someone is really clueless about a topic, if someone knows nothing about economics, then listening to two people, one being a quack and one being the expert, is not very useful. All right, sure, he learns something because he can always take the mean of those two messages, and he knows it's probably better than his prior, because he knows one of them is telling the truth and the other one is saying something at random. The mean is his best estimate. Still, it's not very useful, right? If I listen to a debate between two people and I have no freaking idea who's the expert and who's the quack, and I have no preconception regarding the truth of the subject matter they discuss, the debate is utterly uninformative. On the other extreme, if I perfectly know the state of the world, what's the point of listening to the debate? I already know omega, all right? So I don't get any additional information from listening to the debate, right? The people who stand most to learn about a debate are the people who have a little bit of information to begin with, because those ones will be able to discriminate the wheat from the chaff. They'll be able to say, aha, given what I know, I think Fauci is the expert, and therefore if Fauci says I should get vaccinated, it's probably the right thing to do. All right? And the reason why we're interested is precisely because we wanted to argue that this helps explain polarization in society. People who know more to begin with, they actually learn more from what they read and what they listen to, simply because they're able from what they read to interpret who's more likely to be right, and therefore take that one step further. All right? If I truly don't know whether Fox News is better than the New York Times and they are saying opposite things, I'm not learning much. If my prior is that the New York Times might be better informed, or if I have a prior information about the state of the world that matches somewhat what the New York Times says, I might say, gee, the New York Times probably knows right because it's consistent with my own information, and therefore I might actually take what they said face value, and that gives me more information going forward. All right, so that was part of the motivation of the project. But let me just skip this, and let me just go back. Well, I'll come back to your question just a bit later. Sorry, I thought... how much time do I have left? Not much, right? 10 minutes. Okay, let me just quickly, then I want to go to what you're saying, but let me just say then briefly something else, which is, this was very impolite. You might just go with a polite way of dealing with things. You might just say, I'm just going to ask people to speak publicly, but in turn. If it's private, then it really doesn't matter that it was simultaneous or sequential. The only interesting case is if I ask them to speak publicly in sequence, right? So suppose that I first say, so I'm asking Julien and Rémi, they both know, well, one of them is a quack, one of them is an expert, you guys know, and it's common knowledge among you, but I have no idea, all right? And so suppose Rémi is the expert, just for the sake of the argument. He always tells the truth. All right, that's an hypothesis which we'll have to check ex post. Right? Now, the strategy then for Julien is more complicated because now he's the quack. I don't know he's the quack, but he might find himself in two circumstances. He might be the first one to be chosen to speak, and then he's like, gee, I really have no idea, but I have to look like I know. And the other situation is he comes second, and Rémi says the state is 1/3. And now Julien realizes, damn it, the state is 1/3. I just learned the state is 1/3. Okay? But when you think about it, probably he's not going to say, yes, that's right, 1/3. Why? Because what are the odds that if Julien is right, Rémi as a quack was lucky enough to say the true state? There's 0. So if you hear Rémi say 1/3, you're like, wow, now I know what the state is, but I suddenly cannot repeat the state. Yeah? But I don't want to say something absurd either, because I know that given the state is 1/3, the signal of the judge is between -2/3 and 4/3, all right? So I surely want to say something within that range, right? Because otherwise I would expose myself as a fraud, and surely you and I know it's not something you want to do, right? So, as mentioned, the strategy of the Quack is more complicated, and not shockingly, what the first message will be that he sends will have full support, and the second message he sends will have the property that he says anything within the range of what is possibly consistent given what the expert who spoke first said. So he's going to say something which is possible and which is within one of what Rémi said, because he knows anything outside of that would just not stand a chance of being consistent with what the judge got, and all this is atomless. So let me just, for the sake of time, given that I have only 5 minutes, let me tell you what happens in this game and whether it's good for the expert, for the judge. So the Quack again is, you know, Julien, for the example, is just going to choose uniformly at random. And what's more interesting is that the unique equilibrium strategy for the judge is to go with the first debater, provided the messages are his message is consistent. So if I hear Rémi says 1/3, I might just as well say, shut up, I'm not interested in your message, given that he said 1/3. If 1/3 is consistent, I pick you. If it's not consistent, then I will not pick you, because obviously, if you were the expert, you'd be consistent to begin with. All right? So the equilibrium is not unique, and you might argue that, in fact, Julien did not need to randomize uniformly in case he comes second, because anyhow, the things are already decided to begin with. All right? What really is unique is that the judge's strategy is that the first mover is the one who determines the equilibrium. It's not shocking when you think about it, because as a second mover, you have such an advantage that your credibility is much lower. All right, it's so much easy. It's so easy to be consistent if you're the Quack and you come in second. All right, too easy. So really, what matters is the first person consistent or not? Okay, I don't have time to go into the calculation for why the value of this game is the same as the value for the simultaneous talk. There is no benefit in doing things sequentially, but there is no cost either. Yes, there's none. Let me just say it in one sentence, all right? In the original game, what's the value, right? I flashed the formula here, right? So the judge is not using the uniform tie breaking, but he's indifferent provided the two messages are consistent, right? So the value for the payoff of the Quack is the probability that he's consistent times 1/2. Because in case he's consistent, obviously the expert is consistent, and the judge is indifferent. His payoff is the negative of the judge, so he wins with probability 1/2 in that case, right? The judge is not breaking ties in 1/2, 1/2, but he is indifferent, so his payoff is as if it was 1/2, 1/2, all right? In this game, when does Rémi win? Rémi wins, sorry, Julien is the Quack, right? So when does Julien win? Julien only wins if he comes in first, because if Rémi comes first, Rémi is the expert, then Rémi will say something consistent, he's going to be picked. So for Julien to be chosen, he must be chosen to be coming first, which has probability 1/2, and he must say something which is consistent, which is the same probability as in the original game, same value. Bit surprising, because I thought maybe simultaneous talk would be more valuable, all right? And you would have thought it's more valuable because the second player has less information to work with. You're having players as ignorant as they can, and that sounds like a good idea to incentivize truth-telling. And the reason why I cared about... So it's a little bit disappointing, because I was hoping that this would be a good starting place for a model of debates and how to structure debates. Right? And I'll go much farther now in the last couple of minutes, because I want to really go to Rida's question, which is that the best equilibrium from the judge's point of view? In fact, could I not dream of more complicated protocols? I discussed the simultaneous move game. I discussed the sequential one with one player chosen at random. I could have thought of more complicated one where I first go to Remy and say, Remy, tell me, is the state of the world in the Cantor set or not in the Cantor set? And then I turn to Julien and say, how about is it an irrational number or not? I can come up with crazy schemes, all right? And you could ask, well, you know, we're game theorists. We can come up with crazy schemes. Could we do better from the judge's point of view as the one we described? And the answer is no. The reason is not shocking when you think about it. It's very close to a zero-sum game. So here's the statement that I want to discuss to conclude. It's the best taken from the judge's point of view across all extensive forms. And really, what all I need to do is suppose the judge could commit. Suppose the judge was not constrained by Bayes' rule and could say, you know what, you send messages and you know, we play whatever extensive form and I commit to a selection rule, all right? Then I can use the relation principle for mechanism design. I might just as well say, how about you report everything you know, which is whether you're a quack or an expert, and in case you say you're the expert, what the state is. Okay, and the relation principle tells us it's enough to look at one-shot communication where each player is incentivized to tell the truth. All right, and so of course one of the constraints is that we need the quack to be willing to tell the truth. So he has to be willing to say he's the quack. Yet he could deviate and do exactly what he's doing in a game. He could uniformly randomize. He might say he's the expert and uniformly pick a state at random. And so we have an IC constraint, which is what can he secure by deviating and replicating the marginal distribution of what the expert actually does. The expert tells he's the expert and uses the uniform distribution, but of course the one that matches the state. So I have a simple IC constraint, and it's not hard to see that if both messages are consistent, you know, symmetry consideration mean that there is no way for the judge to favor one player over the other one, to discriminate between the two. So he cannot do better than give a value of 1/2 to the quack in case both messages are consistent, and therefore this gives you a lower bound to what the quack can secure by deviating. And that concludes the argument. You cannot do better than that. And that also concludes my talk, given the little time I have left. All right? In the paper, I look at several more versions that I'm not going to talk about. What if the two players are not symmetric? Perhaps I have some privileged belief that maybe my prior is that Rida knows better than Rida too. We look at the case where, as I said, the quack is not perfectly informed or the expert is not perfectly informed. The last one I want to mention, and I'll leave that as a puzzle, is the teacher's dilemma, which turns out to be equivalent, which is slightly different, which is now the judge knows the state of the world. You know, it's me with those 5 students that are sitting here, all right? I know the answer to the problem set, but I have 2 students, one who's better than the other one. One is a quack. We call it a dunce when it comes to school. He has no idea, okay? And the other one, he's not an expert, but he's better. So I'm the expert because I'm the teacher. I know omega. One of them sees omega plus epsilon, and the other one has no freaking idea, all right? They both write an answer on their blue books, and I have to select which one passes, which one fails, all right? I turn the table, right? Now the question is, you know, you're the quack. What do you write on your blue book, all right? You're the expert, but not perfectly expert. You see omega plus epsilon. What do you write on your blue book? Because your problem is non-trivial as well. Thank you very much.
Yeah, Elena?
No, no need, no need. No, the just wanted to ask if the state is not a number, is like a multiple criterion. Does that like allow some? Does that make it any different?
Repeat that question.
If the state is a vector of features, and the perturbation is like on independent, and the state is independent features.
Yeah, I don't know. It's a good question. Nothing to add. It's a good question. I have no idea. I should say, just to give you an idea of, so, you know, it's not answering your question because obviously I don't know the answer to the question, but my technique is to answer another question. Even if I look at the case minus MM and I look at an arbitrary prior, and even if the expert tells the truth, the bright minds that I consulted are not able to argue that there is the game, the zero-sum game has a value between the Quack and the judge because of this additional states, this additional signal that the judge gets. So I would love to generalize it. And actually, it is an interesting dimension because, I mean, I'm just saying, the question I usually get is, why don't you work on the circle? And I'm like, duh, on the circle it's not interesting because everything is equally consistent. Multiple dimensions is interesting. If I had to guess, I would just argue that if everything is uniform, so if you really think these are all independent copies of uniform, I would just, my guess would be you just do the copy of the strategies multiple times. But I have no idea. It's a good question. It's a good question because when I talk about Cantor sets and real number, and you know, I was just thinking about there might be different dimensions truly that I can interrogate people on. Yes. Yeah. Yes, I mean.
Thank you for the presentation. This model makes me think a lot about an actual game, not a theoretical one, called Undercover. I don't know if you know it. So basically, you have like n-1 experts and one Quack, and then everyone has to vote for who's the Quack. So my question is, how, if it was possible to study this kind of thing with your model, so basically, can you have more than 2 players, so n-1 expert and one Quack, and what would it change if the judges are the players themselves? Maybe the second one is a bit more difficult, but...
They're both difficult, thank you. The first one, so there are 2 versions. One version I didn't talk about at all is when, it's just a slight digression. Here, it was common knowledge between the 2 of you who's the Quack and the expert because I assume that you share the same office and so you know each other pretty well, right? But it could also just have been the case that each of you is an expert for CP and they're independent, right? And I have not solved that game. It turns out to be quite tricky. It's very convenient that there is common knowledge among the players and that everyone knows there is one Quack and one expert. It's a lot harder when these are independent types, to use the word in economics. The reason I mention that is when we have n players and say it's common knowledge there is exactly one Quack, then the game is not very interesting because there is an equilibrium where the n-1 expert tell the truth and the Quack says something else, and it's the majority type of argument with 3 or more, where you can basically perfectly pick who's the expert, just one of the experts, or at least you can for sure prevent, you just say, the expert has no incentive. If 2 of you if the 2 of you are the expert and I'm the Quack and you're supposed to tell Omega, you have no incentive to deviate and I'm screwed, so to speak of. If they're 1 expert and n-1 Quack, it's a little trickier. But you gave me the easy version. Thank you very much. All right. If there is noise, it's a little tricky because even in a case where the experts have noise here, we don't have a closed form. I'm glad I'm running out of time because the talk goes typically downward from here, given that, you know, up to here I could solve closed form, and from that point on it looks much more like pictures. So if the experts are perfectly informed, it's too easy. And if it's common knowledge who the quacks are. But again, end players independent, that I don't know how to solve, all right? Because there is a chance you're the only expert, and so it's a little trickier. Then the other question, yes, the other question is more speculative. What would it mean for the players to vote? But of course, if it's common knowledge among them that they're n-1 expert and one quack, the n-1 expert would just all utter the same word and just basically segregate, or, you know.
In the game I'm talking about, there is a rule that if the expert cannot say exactly the state of the world, they have to say something else. So they can say something close.
Okay, they can't say the state of the world plus they can't say a bijective function of the state of the world? Because that would do the trick as well.
Yeah, I mean...
If you say half the state of the world...
Yeah, I guess it could work, but it's not with numbers in the game, so you
yeah,
can't really do that.
Yes, yes. But point taken, we were quite interested in what happens with more experts and quacks, because one of the arguments is, yes, there's Fox News and the New York Times, but then there are many more medias. And so is it the case that having more sources of information actually makes the problem more difficult or easier? And one might argue that the world was a lot easier when there were, let's say, only one journal, or, you know, Pravda, or, you know, maybe one extreme is, maybe that's too extreme, right? But maybe having only 2 or 3 newspapers might be a lot easier than we have 100,000 blogs, most of which are quacks, so to speak, and you're just a random citizen trying to figure out whether you should get vaccinated or not. So taking limits as n goes to infinity is a very interesting question. We need to find a formulation which is both tractable and non-trivial, preventing these kind of majority games that Rida is very familiar with.
The questions? So I have a last question. So what if the same thing, but you have many judges, they receive different signals, so it cannot be consistent with the, you know, they receive omega plus some signal is I, so now you want to know, and they should vote, majority voting. Yeah. Okay, so one of them should be elected. Did you investigate this one?
Again, it's just, you know, we thought about it. Because just like with the question of Remy, we think it's a very important question, and we really want to think about our judge as the median voter, but that's a little tricky to define in case they all get independent, conditional independent signals, right? So in the draft of the paper we have, we just say, think of him as the median voter, but that's a shortcut which is unsatisfactory. Right, because and the issue, there's another weakness that I didn't discuss. I mean, it's not. We discussed it a little bit. I didn't have time. If I had an hour and a half, I would have gone over that. But heterogeneity in the population is not necessarily about omega. It's also about 1/2, who's the expert and who's the quack. All right. So I have a version that I flash very quickly, where one of them is believed to be more likely to be the expert. And the population is very heterogeneous in this respect, right? Some people still believe that Fox News is a good source of information, and, you know, many people still ask me when I go through customs or immigration, you're an economist, how should I invest my money? They still believe I know something about that, right? So people's belief about who's an expert and who's not an expert. You know, so you were thinking about S as being independently drawn. You might also think about the prior. You have a population, and that's a little easier to work with. But then you really can think about the P here as being the median voter. But the S is an interesting one as well. We have not pushed, but I think our answer is unsatisfactory at that stage. It would be interesting to come up with a version where the population size actually makes the problem quite interesting.
We're going to stop here. Thank you very much, everybody, and thanks to the technical staff too. Thank you.